continue with Chapter 2. In Chapter 2, remember yesterday we talked about motion of the objects, and we talked about the difference between distance and displacement, speed and velocity. Well, today we're going to take a look at the graphical analysis of that motion and what these graphs mean. Now, I cheated a little bit. I actually copied down this graph from one on the internet because I wanted to talk about it and not have my own horrible drawings kind of ruin it for everybody. So we have other ones in yours that we'll analyze tomorrow in class. But I'm going to encourage you, copy this down or sketch it down just so we can talk about it. Now, motion graphs are a way for us to visualize how an object is moving. And so if I look at this graph that's up here, I have a displacement versus time graph. And what it's telling us is that initially this thing is starting off at time 0. It's starting at 0 meters away from the origin. It then is going to change its position. We can tell that by looking at this portion of the graph. It changes its position. And it goes from 0 meters to 2 meters away in 2 seconds. It then, for the next 2 seconds, from 2 to 4 seconds, it's not moving. It's stationary. So if I were to replicate this, it would start right here, and in 2 seconds, it would go 2 meters. It would then stop and hold still for 2 seconds. And then if I look at the next part, it's going to go backwards over the next 2 seconds to go 1 meter further away. And so this motion graph allows us to get an image of what's happening with the situation. Now, what's also nice about this graph is that we can use a property of the graph called slope to give us the velocity. Now, a quick reminder, the slope of a graph is equal to the rise over run. You should remember this from math class. Or, as I like to put it, or as the other way from math class, or I'll do it that way first, y2 minus y1. Let me erase that so it's actually correct. Over x2 minus x1. I will always write it as the change in the y values over the change in the x values. So delta y over delta x. It's still rise over run, or y2 minus y1 over x2 minus x1. But if I look at this, and if I just take these two spots from the very beginning, I'll circle the green, to this part right here, it's going to allow me to find the slope of that particular part of the graph. And I'm going to do that by taking my change in y. So in this case, I can see that it's going to go up by 2 meters. So if I do the slope of this graph, so I'm going to write here, the slope, actually I'll put it down, the slope of that part, my change in y is 2 meters. It goes from 0 to 2, and it's going to do that in 2 seconds. So it's going to go forward, I'll keep it blue, in 2 seconds. And so my change in my x is 2 seconds. Now when I do that, then I suddenly get 2 divided by 2, that's 1. Carry my units through dimensional analysis, meters per second. And all of a sudden I have now found the equation for velocity or speed. So it's telling me that this thing is moving forward at 1 meter per second over those 2 seconds. If I look at the next section where I wrote it in red, it doesn't change. It's at 2 seconds, it's at 2 meters, and at 4 seconds, it's at 2 meters. So its change in y is 0 over 2 seconds, and so that tells me that the object is stationary. That is represented by the graph because it doesn't move. If I go to the next one from 4 to 6, I can tell it's going to have a negative slope. It's going to have a negative velocity during that point in time. Then from 6 to 8, obviously it stays stationary. So the slope of the graph allows us to find the velocity, the slope of the displacement versus time graph. Let me make that clear, because different graphs, well, their slopes mean different things. In a displacement versus time graph, the slope will give us the velocity. Now, this works great, okay, and this is easy, okay, as long as we have a constant slope or change there. Where this wouldn't work if I said, hey, well, could I use to find the slope from 0 to 4 seconds? And for that answer would be no, because there, if I went from 0 to 4, this is what the slope would be, this purple line. And you can tell that's not representative of anything. It would give us the average velocity over that time. And so from 0 to 4 seconds, it goes 2 meters, so their average velocity at that time would be 0.5, but it's not really indicative of what occurred in there. This especially comes as problematic when we have a displacement versus time graph that doesn't have straight lines. And so you can tell, and I'm going to showcase this, if I were to look at 1 second, if I were to find the slope of the graph here, it would look like this. If I were to do it at 4 seconds, I'll put this in orange, it would look like this. And so you can tell that the slopes of those graphs are different, which means that these two spots have different speeds or velocities, because the slope is the velocity. And so in this situation, we have a case where if you find the slope of the graph at 1 second, that's going to give you the instantaneous velocity, the speed at 1 second. But that's going to be different than if you find the slope at 4 seconds, because now it's going to give you a different speed. A great example here would be like, let's say you are traveling from your house to your grandmother's, and let's say that it's 50 miles away. And let's say it takes you 1 hour. Well, your average speed, 50 miles divided by 1 hour, is 50 miles an hour. But that doesn't mean that you travel the whole way at 50 miles an hour. You know, you're going down Fairmount, you're probably doing about 40. You get out of the expressway, you're doing about 70. You get stuck in traffic, you're doing about 2. So your instantaneous velocity will change from bit to bit, where suppose your average would be, you know, across the entire grid. Now, because there's a change in that velocity, we actually have another name for this, and this is called acceleration. Acceleration is that change in velocity over time. In fact, I'm going to give you now your second equation that's on your reference tables. The acceleration is defined as the change in your velocity over your change in time. And again, this is an attempt to, once again, just explain how objects move. We've already talked about, we can talk about their change in position. Okay, it was here, now it's here. Yay, that's great. Well, how much time did it take? That'll give us our speed. We traveled to 50 miles in 1 hour. Okay, great. The acceleration tells us by how much will that speed change. Oh, he was traveling at 2 miles per hour. Now he's traveling at 50 miles an hour. Now we can find out how much that changed by and how long it takes. One of the big things on cars is it goes 0 to 60 in 2.4 seconds or whatever. Or, you know, in my case, my car, in 13.6 seconds. Okay, so that gives you the acceleration. What's the jump off line? How quickly will it change its speed? Now, the acceleration can also be found via a motion graph. Now, if you look at this graph, and again, I cheated a little bit. I already snagged this off the internet. But this is giving me, instead of a displacement versus time graph, it's giving me a velocity versus time graph. So it's telling me, how does my velocity change with respect to time? So if I look down here, initially I start off, I'm at the line, I'm traveling 0 meters per second at 0 seconds. Okay, I then push down the accelerator, and now my speed increases. It goes from 0 meters per second to 8 meters per second, I'll put it in orange, in 4 seconds. And so my speed has increased. Okay, and because I know that the change in the velocity of the change in time is acceleration, I can, once again, use my slope. My change in my y over my change in my x to solve for this case, the acceleration. Now you'll notice, you're like, but wait, didn't you just tell me that the slope of the graph was velocity? It is for a displacement versus time graph. But since this is a velocity versus time graph, that slope tells us something else. And so you always have to look, what is my graph giving me? And then so, does the slope give me something else? Does the slope give me something meaningful? In this case, it's going to tell you that my change in my y, in this case, 8 meters per second. And I'm going to do that in 4 seconds. And so there's my change in my velocity. Actually, I write that up, delta v over delta t. So this is going to give me 2 meters per second, or you'll hear me often say it's meters per second squared. We'll talk about that tomorrow as well. Now, turns out that there's also something else you can use a velocity versus time graph for. And I'm going to scroll down. I'm once again going to use the exact same graph as what we used up top. Again, I've got to cheat again. But now this time I want to focus on a second part of it. I want to focus on just this section right here. The spot where it says that I have 0 acceleration. And I want to talk about the area that's underneath there. Now, in this situation, I'm going to find the area that is underneath that particular part of the graph. And so I look and see what shape it is. And I say, oh, okay, that's area. The area is equal to base times height because it's a rectangle. Well, if I look at my base, my area is 3 seconds. Sorry, not my area. My base is 3 seconds. My height is 8 meters per second. So what that's telling me is that this object is traveling at 8 meters per second for 3 seconds. Now, if I go back and if I just put this on, this 3 seconds, this is a time. This 8 meters per second, that is a velocity. And if we go back and look at our equation for velocity, velocity times time will give us the displacement. Which makes sense because you say, oh, well, wait a minute, okay. Well, if I'm going 8 meters every second, after 3 seconds, I will have gone 24 meters. And so the area underneath that curve is equal to the distance traveled, or the displacement of the object. Now, if I look at this other one, and this will be the last one we'll call it a day, if I look at this piece, this one's a triangle. And so the area of my triangle is equal to 1/2 of the base times the height. And so in this case, I'm going to go 1/2 of 4 seconds times 8 meters per second. And that's going to give me 16 meters. You're like, okay, I travel 16, but that doesn't make sense. But go back to this. Remember how we find the displacement. We take the average velocity times the time. Well, the average velocity goes from 0 to 8. So the average velocity is 4 meters per second. My time is 4 seconds. Well, if I travel for 4 meters per second for 4 seconds, that's going to allow me to go 16 meters. So we'll practice with this tomorrow in class, and we'll get a little better handle on it. So everybody have a great night. Talk to you later. Bye.